See, using kinetic theory of gases, we should be able to predict or prove what is PV is equal to 1 by 3 mnc square. Average kinetic energy will turn out to be 3 by 2 RT, and RMS will come out to be root of 3 RT by M. Okay. We can derive that, uh, using this simple fundamental. Consider a particle present at one corner or on one face of a cube. From here, as it moves towards B and comes back. Okay, so this is one particular collision in X direction which it is making with the walls of the container. So considering this simple fundamental, we should be able to find out what is the pressure which is being applied by that particle on this face B. See, we can check out the momentum which it is carrying, before the collisions is m into ux. After the collision, it is minus mux. The change in collision would be 2 times of mux. Okay, so this minus of minus this, so that will be 2 times of mux. This is the change in momentum. And the distance traveled from A to B and coming back to A, that will be this L distance twice of it. So 2L distance. So the distance traveled is almost 2L. Then how many collisions does it make per second? So which means time taken would be distance traveled per speed. This is the time taken. So number of collision is per time. So per time as in 1 by t, which will be ux by 2L. So we'll be using that. So number of collisions per unit second with the wall would be ux by 2L. This is the change in momentum. So change in momentum per unit time will give us force. So change in momentum delta P by delta T. So this change in momentum we have already calculated. So 2mux per time is this one. So you will get this as the force. So mux square by L is the force applied by that particle. So the total force that is impacting on that particle on the wall, by that particle on the wall, is mux square by L. Pressure would be force divided by area. So area is L square. So mux square by L cube. So this is what you will get as pressure. And L cube is the volume. So PV is equal to mux square. Now till this point, you should be able to understand easily using the derivation. But from here, I want you to know the terms carefully. Check out. P into V is equal to mux square. What does this ux square means? Which means it is the speed of the particle in x direction. And this is about one particle. Suppose if you have certain n number of particles, then this is what it would be, that every particle will give certain amount of pressure. The total pressure will be sum of all of that. So pressure Pt of x will be m by v, I is equal to 1 to n, uxi as in it would be the sum of u1 square plus u2 square plus u3 square and so on. So sum of all of these speeds multiplied by m by v multiplied by this m by v will give us pressure. Now we can define an important term called what is the mean square speed. Mean square speed ux square will be equal to sum of all the speeds, with square of it divided by total number of particles. So this will n is the total number of particles. So this u square and this entire sum, that is this one. So that can be replaced by n times of this mean square. The minute I have written this bar, it means it is a mean square speed. So u square x, with this bar means it is a mean. So the total pressure will be m n by v into u square bar.
So can you repeat mean square speed?
See, by definition, mean square means ux square in x direction. If there are n number of particles moving, then that would be u1 square plus u2 square plus u3 square and so on up to un square. All of that mean I'm taking, which means by n number of particles we have. Okay, beta.
Got it, sir.
Can I write all of this as sum of 1 to n here, summation 1 to n, and
Yeah.
this n I am multiplying with this. So this summation of all of this will be equal to n times of this.
Yeah.
So uh, this entire term I'm replacing with that n times of u square mean.
Okay. Got it.
And we know that pressure in gases, whatever the pressure which is applied in this direction will be same as this direction, and in fact in all the directions. So whatever the pressure, that is average pressure, which is applied on x direction should be same in y direction, should be same in z direction as well. Okay. And if you see ux square, if this is the mean in x direction, the same amount of mean should be in the y direction, same amount of mean should be in the z direction. So considering that, because all, if you have a random particles and you make some average in x direction and you're getting certain value, the same average you will get it in y direction, same average you will get it in, x direction, y direction and z direction. So if you write something like this, imagine a particle is moving, right? A particle is somewhere here and it is moving in 3 dimension, right? Then what all this, if at all I try to find out the mean of those particles, then what I can do, I can write its x component, y component and z component, right? So can I write this u square bar, which means mean for a particle moving in 3 dimension, will be its x component plus y component plus z component. And since all these three are same, I can write it as 3 times of ux square bar. So ux square bar is equal to 1 by 3 times of u square bar. So u here is the speed of a particle in all the directions. So therefore, if I can replace this, you can see u square bar. If I replace that by 1 by 3 times of u square, so then I will get this as 1 by 3 mn u square bar. I guess all of you understood that,
Yes. Sir.
right? So what is the mean square speed from here? You can understand that. So mean square speed, considering you have n number of particles, so u square bar will be u1 square plus u2 square plus u3 square and so on up to un square by n. This u1 means there is a particle 1 which has certain speed u. Okay, there is a particle 2 which has certain speed u2. There is particle 3 which has speed u3. So if you take sum of all of that divided by n, you will get a mean square speed. Okay. Now see, total kinetic energy. Total kinetic energy will always be equal to half of m into u1 square plus u2 square plus u3 square, right? Because sum of all these particles, if we take half mu square, we will get total kinetic energy. And just now we got that u square into n will be equal to this. So instead of this, I'm replacing with m into u bar square. Now we know PV is equal to 1 by 3 mn u bar square and kinetic energy is equal to half mn u bar square. So you can equate these two. I mean, in case if you check out the total kinetic energy, we can relate these two and get different, you know, derivations. For example, if you check out total kinetic energy, I can write this as 3 by 2 PV, because this half into mnu square can be replaced here with kinetic energy. 2 times of it. So therefore, total kinetic energy will be 3 by 2 PV. PV I can write it as nRT. So 3 by 2 nRT. So total kinetic energy is equal to 3 by 2 nRT. What important part here is it dependent on both. Here you can see this kinetic energy, total kinetic energy depends on both N as well as T. Total kinetic energy will always be dependent on number of moles as well as the temperature. Now, if you see average kinetic energy, it is the total kinetic energy divided by the number of particles, because if you have some 100 value as the total kinetic energy, if you want to find out per molecule, so you just divide it by the total number of molecules, correct? So if you have n number of molecules, total kinetic energy by n will give you average kinetic energy. This average kinetic energy is of one particle, okay? So that will be 3 by 2 nRT. Number of particles, I can write it as n into Na, because number of moles, we can write it as n by Na. N is the number of particles divided by Na is the Avogadro number of particles. So n can be written as n into Na. So I'm just replacing this n with n into Na. So this nn will get cancelled. I'll get it as 3 by 2 kT. So another very interesting thing is average kinetic energy does not depend upon number of moles. It only depends on temperature. Okay. And here this R by Na which you are getting, we can replace that with a new constant called Boltzmann's constant, R by Na, which is 1 by 3 into 10 raised to the power of minus 23 is what you will get. Okay. So this is a very important note, everyone. I suppose you should remember this. Total kinetic energy depends upon N and T, while average kinetic energy of a particle depends only on temperature. Okay. And now coming to the root mean square, URMS can be represented as the root of, square mean here. So URMS will be equal to root of, this is square, mean square speed, correct? So these are the summation of all the squares divided by n, which gives us the mean. So total kinetic energy is written as half into mnu square, which is equal to 3 by 2 nRT. We just derived this earlier. Now I can write this as 3 by 2 nRT is equal to half into mu square. If you check it out here, this n will get cancelled. And another important thing is this m into n which is there. This m is a mass of single particle. N is the total number of particles. Got it? So using this relation, we can get this. I hope you understand this. M into n can be replaced as m by na into n into na, which is m into n. Where it is coming from, think this way. Number of particles, I can write it as n by na, okay, and mass into n. This will give us number of particles, molar mass by m. This would give us number of moles. So now you can see that if at all I can write it as m by m. M is the molar mass. Molar mass is represent. We know that molar mass is represented for 1 mole of it. So if you have m mass of a particle, got it? Then this is for one single particle, got it? So for single particle, whatever be the mass, single particle mass into n. So this give us the total mass, right? So this total mass divided by m, that should give us number of moles. And number of moles, I can write it as n by na. So this n, if at all I replace by n into na, right? So I would get that m into n is equal to m into n. Remember, this and this are different. M is the mass of single particle, n is the total number of particles. M is the molar mass, n is the number of moles, right? So this m into n can be replaced by this m into n. So if at all I replace that here, this m into n, I'm writing it as n into m. So this nn will get cancelled. So RMS will be equal to 3 RT by m. And if you take root of it, right, this is what we call it as RMS speed, which we will derive it as 3 RT by m. So what are the takeovers from here? One is the RMS speed. Second thing is how to put total kinetic energy. Okay. Second, this is a very important note. What is the average kinetic energy? And its value is 3 by 2 kT. Okay. Next important takeover from here is PV is equal to 1 by 3 MNC square. So these are some important pointers you should get out from kinetic theory of gases. Not that these derivations are important, but the application of this, all of these terms is very, very important for exams. URMS can also be written in terms of pressure and density this way, because PV is equal to nRT. I can write it as PM is equal to dRT. So this RT by M can also be replaced by P by D. So URMS can be written as 3 times of P by D. Okay. Now, what are the types of problems we will get? Let's see, and what we usually face the problems. Let us, for instance, if you have a simple question here like this, calculate the pressure exerted in ATM by 10 grams of O2 in 2 liters container, given URMS is 200 meters per second. See, for pressure, all we know that PV is equal to 1 by 3 mn c square. This is what we know. I can write this as c square, or originally how it was, which is u bar square. Now, here, if you check out this m into n, that is the total mass of that gas, which is already given 10 grams of O2. So this mn itself is 10 grams. So which means pressure would be equal to 1 by 3 times of 10, which is in grams. So I have to convert that into kgs. So 10 raised to the power of minus 3 into U square. URMS is given. RMS square would give us this mean square. So that would be equal to 200 whole square. That divided by volume. Volume is given 2 liters, but as per the units, we are taking everything in SI system. So 2 into 10 raised to the power of minus 3. Okay. So I guess you understood that. So one of the 2 will get cancelled here. So we will have this as 2 by 3 into 10 raised to the power of 5. Okay. And if you want that in ATM, I would be dividing this term 10 raised to the power of 5 into 1.013 into 10 raised to the power of 5. Okay. So it is approximately, right, which is approximately 2 by 3 ATM. So I want all of you to understand the unit conversions carefully. Got it? You have to do everything in SI system only. I guess all of you understood that.
Can
Yeah.
you explain again?
Okay. Check beta. We know the equation PV is equal to 1 by 3 mn c square. 10 grams of O2, which means this is the total mass of O2 in the system. Total mass is nothing but this mass of a single molecule multiplied by total number of particles. So m into n is the total mass of the gas given, which is given as 10 grams already. So I have to convert this 10 grams into kgs. So 10 into 10 raised to the power of minus 3 multiplied by mean square speed. Mean square is RMS is given as 200. RMS square will give us mean square. So 200 in square of it. Then 1/3 into mn. This is the mn value. This entire thing is mn value divided by volume. Volume is given as 2 liters. So I have to convert that liters into meter cube. You know that 1 liter is equal to 10 raised to the power of minus 3 meter cube. So I'll use that fundamental here. So 2 into 10 raised to power of minus 3. So this 10 raised to power of minus 3 will get cancelled. I have 10 raised to power of 4 here into one more 10. So 10 raised to power of 5. This is 2 square. 1, 2 will get cancelled. 2, there is one 3 carried here. So 2 by 3 will be coming. Now all of this what we got is in Newton per meter square or Pascals. This is in SI system. And we know that 1 ATM is equal to 1.013 into 10 raised to power of 5 Pascals. So I have to divide this entire thing by 1.013 into 10 raised to power of 5 so that it will convert into ATM. Is that clear, beta?
Yes, sir. Thank you, sir.
Check out the next question. First, I'm doing simple ones so that you can understand the uh, units carefully, okay? Calculate the URMS of N2 gas at an altitude of 20 kilometers where the temperature is 200. Okay. So basically here the importance is only about temperature because you know that URMS is equal to under root of 3 RT by M. Okay. Now while doing it, just check out the units carefully. Everything I have to put it in SI system. So R should be 8.314 into temperature, which is 200, divided by molar mass of N2, which is 28 gram per mole, right? So I have to put it in kgs per mole. So this will become 28 into 10 raised to the power of minus 3. So just notice the units. That's all is important here. Okay. So molar mass should be written in kgs now, not in grams. So when you solve for this, you'll get approximately 422 meters per second. Okay. Everything is in SI system. I guess you got this, everyone.
Yes,
See the
sir.
next one. Calculate total kinetic energy of a sample of 10 grams of hydrogen gas at a temperature of 27 degrees centigrade. See, the minute you see the word total kinetic energy, because total kinetic energy depends upon both number of moles as well as temperature. So first calculate number of moles, which is 10 by 2, which is 5 moles. Okay, so we got number of moles as 5. So we got 5 moles here and temperature is given already 27 means temperature is 300 kelvins. So we just have to substitute that here. So what do we get? So total kinetic energy is equal to 3 by 2 times of 5 into 8.314 into 300. So this is what you will substitute. Okay. So on doing that, approximately you will get this as 18.7 kilojoules. Okay, because everything is coming in joules, so you take 1000 out, that will become 18.7 kilojoules. Again, check out the unit conversions. Do not put anything like kilomoles. Okay, the SI unit of moles itself is moles, it is not kilomoles or something, so you have to just put in moles. Weight you have to convert into kgs, but not with the moles. Everybody got that? See the
Yes,
next.
sir.
Okay, see the next one.
Just a second, can you show that once again?
Yeah.
Okay, sir. Thank you, sir.
See the next question. Calculate average kinetic energy per molecule, then the pressure exerted, temperature of the gas in the same temperature of gas in the same is the same as that of oxygen gas having mass 64 grams is kept in a container of 22.4 liters having a mean square speed of 400 meters square per second square. Here it is directly given mean square speed. It is not root mean square, means it is u square value, right? So it has been given u2 square, sorry, u square here, that is given as 400 meter square per second square. U, which is mean square speed, u bar square is 3 rt by m. right? Because the root won't be there, which implies temperature would be U square bar into M by 3R. Okay. So the minute you come across this, I would recommend first always calculate temperature, which makes your next step very easy. So if you calculate the temperature, this is given as 400 already. Okay. That multiplied by molar mass. Okay. Now see the molar mass. This is about oxygen. So that would be 32. Now this is in gram per mole. I have to convert that into kgs. So into 10 raised to the power of minus 3 divided by 3 times of 8.314. So again, careful with the units. Got it? So you do this, approximately you will get a temperature of 0.513 kelvins, almost close to 0 kelvins. Got it? So this is a temperature which you will get. So once you calculate the temperature in kelvins, rest of the things would be easy. Now you see, we wanted to calculate what is the average kinetic energy per molecule. If you check out average kinetic energy per molecule was found to be 3 by 2 into kT. It does not depend upon number of moles. And the value of K is 1.38 into 10 raised to the power of minus 23. So that would be 3 by 2 times of 1.38 into 10 raised to the power of minus 23 into temperature 0.513. So that comes to be 1.06 into 10 raised to the power of minus 23 joules. So this is what you will get, average kinetic energy. Now, last thing is about pressure. Now pressure we can calculate using this formula, which is PV is equal to 1 by 3 mn c square. Either this, or we can simply use PV is equal to nRT, because the rest of the data is known to us now, because I already calculated temperature. Volume is given here, is kept in a container of 22.4 liters. Got it? So rest all things are given here. So we should be able to calculate using PV is equal to nRT. So nRT by V. This time for calculating the pressure, definitely we need the information of the gas. So this gas is same as oxygen, having mass of 64 grams. So now we know the mass of that gas. So therefore number of moles of the gas will be 64 divided by 32. Right. Next, so we know the number of moles here. Temperature we just calculated as 0.513. Volume is given 22.4 liters. Alright. Here, check this. I want answer in ATM. Temperature, pressure, I want in ATM units. Then what should be the R taken? The R we should take it as 0.0821. Alright. So depending upon what is our need, accordingly you use the units. So therefore number of moles is 64 by 2, 64 by 32, which is 2 times of 0.0821 into 0.513 divided by volume, which is 22.4 liters. So I guess all of you understood how to use the units. So that would come as 0.003718. This is Maxwell's-Boltzmann's distribution curve. Right? First of all, let's see what is the basic assumption. The speed of the molecule of a gas changes continuously as a result of collisions. Therefore, we always talk about average speeds, which means if a particle starting from here make a collision with a speed u1, then again after the collision it changes its speed. After again a collision it changes its speed. One more collision it changes its speed. So the speed of the particles will continuously keep changing every second. I mean every time it makes a collision. So it is always be important to talk the average speed rather than the individual speed. Second, the observed properties like pressure, average kinetic energy do not change with time. Okay. So it is expected that it would be possible if number of particles between any two definite range must remain constant even though the speed of the individual particle may change, which means this average which we are drawing out of it, like we have drawn URMS, total average kinetic energy, only kinetic energy average, got it? Pressure, they do not change as long as you keep temperature constant, as well as uh, you know no matter how much you keep it for long time, so it is not going to change with respect to time. So we will be discussing about these terms more than individual pressure, individual speed and so on. Okay, so these are the important assumptions while talking about Maxwell's Boltzmann's theory. Now coming to this, suppose, okay, before getting into that, you know how your distribution of marks would be usually. Okay, suppose in your class there are 100 students. Okay? So out of those 100 students, not everybody would get similar marks. One might get 90, one might get even 10, one might get, some 3 4 students might get 20, some students might get 50. So this way, if you check out between two certain marks, for example 55 to 60 marks, between this range of marks, let us assume there are a total of 20 students. These are around 20 students. Like that, if you distribute the entire division of marks, correct? That's how we do usually give the grades also. Like 0 to 5 marks, 5 to 10, 10 to 15, 15 to 20. Like that, I've made up to 100 from 5. Okay, 0 to 5, 5 to 10, and so on. I made this into different categories, and every time I'm finding how many number of students are there. 0 to 5, there is only one student, got it? And 5 to 10, there are 20 students, like that. So then 10 to 15, there are 30 students, like that. If at all I keep plotting between the ranges of marks versus the number of people present in that range, this is called distribution of your class, correct? This is called the average distribution of the class. I guess all of you understood what it is. Okay. So the same thing, if at all I make a distribution of speeds versus the number of particles, various different speeds between 5 meters per second to 10 meters per second, how many gas particles do we have? 100 meters per second to 200 meters per second, how many gas particles do we have? Like that, if at all I put the distribution with respect to number of particles, that is called the distribution of gas. Most of the time, a random sample distribution, random sample as in having different, like for example in your class, if the marks range are ranging right from 0 marks up to even 100 marks, all almost all different values every student has got. So that is called a random data. Whenever we have a random data and we make a distribution out of random data, we usually get something like a bell curve. This is called a bell curve. A very familiar curve you'll be using a lot in maths, going ahead also. In engineering, we'll be again using this a lot of times, okay? Especially who are doing statistics, they must understand better. So the point is, here you will get some distribution curve like this. Now for this, if at all I represent that in a mathematical format, I will get a formula. And that formula is this, right? What does this mean? If at all I take particles between u and u plus du, okay, speed is u and u plus du. Between this range of speed, how many number of particles do we have? Dn number of particles. So this is a generalized formula for distribution pattern. Everybody got this? This is called Maxwell's Boltzmann's distribution curve. So check out, dn is equal to 4 pi n. N is the total number of particles. M molar mass divided by 2 pi RT to the power of 3 by 2 exponential of minus m u square by 2 RT into u square into du. Okay. So basically this expression is telling us the total number of particles having the speed range of u and u plus du. I hope all of you understood that. Now, this term can also be written, in various different formats. For example, the same equation, if you observe, there are two functions present in it. One is exponentially decreasing function. The other one is u square. These are all constants. What does this u square represent? A parabolic function. Exponentially decreasing function is also present with it. So I'm getting two functions here, which I'll write it this way. 1 by n dn by du is equal to 4 pi m by 2 pi rt to the power of 3 by 2 u square into exponential of minus m u square by 2 rt, right? This is what you have. Now, what I'm doing, observe carefully, this entire term which is there, this entire term, I'm taking it as a constant value and I'm assigning this as some a. And here also this entire term m by 2 rt, I'm assuming this as b. And this entire term here on the left hand side here, this I'll take it as some y. So I can take this as y is equal to 4 pi a u square into e raised to power of minus b, sorry, this I'll take it as x. So 4 pi a x square minus b x square minus b x square. Can I write this? Everybody understood that? So y is equal to some constant into x square multiplied by e raised to power of some constant into x square. So one is the exponentially decreasing function, the other one being an parabolic function. Okay, guys. Now, if you observe this a value and b value, both of them are dependent on m by t ratio. So a and b both depends on m by t value. Okay, what is this dn by n? Dn was the particles, between present between u and u plus du. Dn by n means fraction of particles present. So let me write down that. So dn by n represents fraction of particles, present between u and u plus du speed. Okay, suppose if at all you see for molar mass m and constant temperature T, as we can write this graph as 4 pi ax square into e raised to power of minus bx square. These two functions, this part is a parabolic part, this part is an exponentially decreasing part. You know that parabolic part will go like this and exponential form will go like this. Exponentially decreasing function will go like this. Okay. So what you will observe here at low speeds, okay, generally at low speeds, parabolic function is always more dominant. Okay, so this value almost reaches to 1 because at low speeds, which means this x value is very small, this will be e raised to power of minus some small value, which means it is tending to 1. So ax square will be more dominant function at lower speeds. But higher speeds, this value becomes so, the upper value becomes so big in negative that it will become almost 0. So this will try to drag down to 0. Got it? That's why overall function will have first a parabolic part and then an exponent part which is dragging towards 0. So this part is that parabolic part, this part is that exponent part, and always gives a maxima at some point. Okay. So see what I am plotting on y-axis and what I am plotting on x-axis. Y-axis it is dn by n into du. This is the y which I have used here, that versus u. If I use this, correct, then what about anything under this area? Check out area under this curve would be what? Suppose if this is a du amount, small change, that multiplied by y. What should I get it? I should get area under this curve. So what am I getting here now? So dn by n du multiplied by du will get us dn by n, which is fraction of particles present, in total number of particles, which is dn by n. Like this small fractions, if I add everything, what should I get? I should get area under the curve, complete area under the curve. And how much that will be? That should be equal to 1. Let me show you that. Suppose if you check out area of this rectangle, area of this particular rectangle, that will be dn by n. We just proved that. Suppose if it is about one particular range here, okay, so like this, I'm taking small ranges, this one, and I'll take this one, and I'll take here. Like this, if I keep on adding all small dus, I should get the overall number of particles present per total number of particles. That's what we have done here. So suppose if at all I take small range of du from u1 to u1 plus du, then let's say the number of fraction of particles is dn1 by n. Similarly, if I take range from u2 plus du, then fraction of particles, I took it as dn2 by n. What will be the area under this curve? Area under this curve will be dn1 by n, this fraction plus further fractions. If I add all these fractions, what should I get? Above all the fractions, if you combine, it should come out as n by n. So it should be 1. So that's why the area under the curve, when you check out, it should come as 1. The same summation, if I write in terms of integration, what would I get? 0 to infinity. If I add all those small, fragmentations by n, it should come as 1. I guess all of you understood this. Using this concept, we should be able to calculate other types of speeds, which includes what is the most probable speed, what is the average speed, and so on. Most probable speed should be equal to root of 2RT. So how do we do this? You can simply use this equation. Y is equal to ax square into exponential of minus bx square. We know that most probable as in the speed where it is maximum number of fragmentations you are getting, or maximum number of particles you are getting. So this is that u most probable. So at this point, the first differentiation will be 0. So at maxima, derivative will be 0. So you differentiate this. On differentiating that, we will get something like this. So dy by dx is equal to exponential of minus bx square into 2ax plus ax square exponential of minus bx square into minus 2bx is equal to 0. So if I take this common, exponent minus bx square into 2ax, if at all I take common, I'll get this as minus bx square plus 1 equal to 0. So x can be equal to 1 by root b, which is equal to under root of 2RT by m. Okay. So that's how we would get this as u most probable will be equal to under root of 2RT by m. One thing you can notice is that most probable is in fact less than u RMS, which is root 3RT by m. Now, what are the type of questions? This year also, year 2020, there was one very good question in here in advanced, which is based upon these fractions. So you got to understand how these fractions work. Check out this question now. Find the fraction of particles whose speed lies between u most probable to u most probable plus du. Okay. This year it was made even more complex with adding a fraction here. I'll show you one of the questions like that. Check out what it is. Dn by n, what we know by the formula is 4 pi m by 2 pi rt raised to power of 3 by 2. Okay. Then exponent of minus m u square by 2RT into u square into du. This is how it was. Now, instead of this u, what he's saying, what if it is most probable speed, with small gap of du? So, in this du, what are the fraction of particles present? So, what I will do, I will replace this u square with its value. Okay. So, what is the value of that? So, u square is 2RT by m. Here also it is 2RT by m. Okay. So you can see in the exponent everything is getting cancelled. Will get cancelled here. 2RT and 2RT will get cancelled here. So what is left out here? We will get this as 4 pi into m by 2 pi RT whole raised to power of 3 by 2 exponent minus 1. So what everything is getting cancelled out there. Multiplied by 2RT by m into du. Okay. Now this RT by m, I can bring this inside this as well, because this is m raised to power of minus 1. So m raised to power of 3 by 2 minus 1. So that will give m raised to power of half. And same 2RT also I can put it down here. So therefore I will get this as only pi I have to remove it out. So 4 pi by pi of 3 by 2. If I bring that, rest will be m by 2RT whole raised to power of half into e raised to power of minus 1. So this brings at 4 by root pi, because this pi, if at all I take it down, I will get this as root pi into root of m by 2RT, root of m by 2RT into 1 by e. So this is what you will get, right? Same thing, you should be able to calculate the fraction of particles for u RMS speed in the same formula. Instead of m by 2RT by m, this time you will put 3RT by m. Okay. So when you put 3RT by m, I'm directly writing the final calculation which we will get. dn by n, which you will get, will be equal to something like 4 pi by 2 pi whole raised to power of 3 by 2 into m by RT whole raised to power of half, okay, into 3 times of e raised to power of minus 3 by 2. This is what you will get. So I think you should be able to figure it out. Just introduce this, instead of 2RT by m and 2RT by m here, write down 3RT by m. You should be able to get it. Okay. So I'll show you how this year's question was. Okay, and usually how the questions, tricky questions will be asked from here. Another thing, there was one year in 2016, it was based upon the definition of average speed. Please understand what is an average speed. Now imagine if at all I have to make an average of all your marks in the school. Okay, in your class there are 100 students. Now I'm trying to average it. There may be students who got a similar score as well, right? Some students might have got 10, some student might have got 20. So what I'm doing, see, 5 students got 10 marks, 3 students got 20 marks, 15 students got 40 marks, plus, and so on. Like this, what I'm doing, I'm taking, these are clusters of marks. So this 5 students, 3 students, 15 students, okay, multiplied by these respective marks, got it, all divided by total number of students, which is 5 plus 3 plus 15 plus so on, correct? This is averaging. I hope all of you understood that. This is a simple mean average. So I'm writing the same thing for u average here. U average is equal to dn1 into u1, fraction of particles, sorry, number of particles, small number of particles having the speed of u1 plus dn2 u2 plus dn3 u3 and so on, divided by dn1 plus dn2 plus dn3 plus and so on. This should be the average speed. If I write as a summation of this, can I write this as summation of I is equal to 1 to some p. P is the total number of parts like this, that is dni into ui divided by summation of I is equal to 1 to p dni. What happens if you add all the number of students? We should get the total number of students always. So therefore, below I will get it as n only. Above this summation, if at all I put in terms of integration, so this dn will become even smaller. So this dn becomes smaller and smaller. So which I can write this as integral of 0 to infinity. Imagine there are so many parts of it, will become u into dn. So that would be equal to, now what I have to do is 0 to infinity here, which is 4 pi n, the root of m by 2 pi rt raised to 3 by 2 exponent of minus m u square into u cube into du divided by n. So if you do that integration, you don't have to do that, you know how it is. You just have to worry about the result. So it will come out to be 8 RT by pi n. So this will be the U average. Everybody understood that? How to get it? Now, just like how we have done it for most probable speed and RMS speed, do the same thing for average also. This you will finish it. Okay, I'm leaving it as a blank. You better try that. Put that entire terms here properly. Instead of 2 RT by m, this time we'll put 8 RT by pi m, and accordingly see how many fraction of particles you will get. Okay. Now this year's question was based on this, and this is another very important type. Now here this year also there was a question based on this fraction. Instead of C, I could have used this as U most probable plus, right? Sorry, U most probable to Q most probable plus DU. This is what we have solved. What if instead of giving du, he has given some fraction multiplied by urm, u most probable. Got it? So this in fact was du what you were discussing. So after solving everything, let us imagine we got this. So imagine we got till this point. Okay. Now instead of this du, I have to replace that with what? F times of u mps. Everybody got this point now? This f is a fraction which is present between 0 to 1. Okay. So, which means I will write this as 4 by root pi into m by 2 rt multiplied by 1 by e into f into urms. Urms is under root of 2 rt by m. Okay, this is 2 rt by m here. Okay. Now, if you observe this 2 rt by m and this m by 2 rt, everything will get cancelled here. So what do we left out? We'll be left out with only 4 by root pi into f by e is what you left out with. So while doing the fractions given, so one best part you will get this is dn by n will be directly related to the number of fractions that are being given. Okay. So most of the time you will see all of these terms m by rt, this will get cancelled with the other term which you have used. Okay. So rest all things will get cancelled and dn by n will be only proportional to f. Yeah, you guys understood that? Right. So this was one of the match the columns which was given, in JE before. So what it was, see this and work carefully. You have to work out. I'll just give you the hint. You have to find out a ratio of dn by n lies between most probable to most probable plus du. This is the first one with RMS to RMS plus DU. So first two questions which we have worked out, उन दोनों का ratio लेना है. These two, this one and this one, ये दोनों का ratio. This was the first part of the match the column. Second, ratio of dN by N of oxygen and sulfur dioxide gas lies between URMS to URMS plus DU. So URMS once apply for oxygen, which means molar mass, write it as 32. Second time write molar mass as 64. Then check out the ratio between those two. कितना आएगा? Suppose all of you understood that. Next, dN by N of oxygen and sulfur dioxide with most probable this time. Same question with most probable. Last question, dN by N for oxygen and sulfur dioxide gas between U average plus 0.5 U average.
So,
Understood? Yeah? Yes.
could you repeat what you said for the third one?
Third one.
It was again thoda.
Okay. Second one and third one are quite similar. यहाँ पर RMS यूज करना है, यहाँ पर मोस्ट प्रोबेबल यूज करना है. ऊपर जो भी हमने डिराइव किया है वो आप एक बार उसमें मोलार मास में ऑक्सीजन का मोलार मास रखोगे, एक बार SO2 का रखोगे और दोनों का रेशियो लोगे.
Okay, got it.
Last one, dN by N for oxygen and sulfur dioxide. Between these fractions, one very interesting point what we have noted down that dN by N when you take out, तो वो सब कुछ कैंसिल होके सिर्फ इसी टर्म में बच जाता है ना, फ्रैक्शन के टर्म में बच जाता है. सो इट विल ओनली बी डिपेंडेंट ऑन फ्रैक्शन. सो इफ यू आर आस्किंग फॉर द सेम फ्रैक्शन, दोनों के लिए सेम ही रहेगा, बाकी सब कैंसिल हो जाएगा. इज दिस क्लियर? सो इस इनफैक्ट इसका आंसर 1 आना चाहिए रेशियो निकालोगे तो. I guess all of you got this. I am leaving some space again here. You have to properly write and calculate. Okay. ऐसे typical, ये वाला एकदम typical type of question है. So this is the area you should focus more and try this. I guess all of you will do that. Yeah. Match the correct answers out of it. Okay. Right. Now coming to the application of the speeds, U RMS, U most probable and average. Where do we use this? First of all, if you see the value wise, if you check it out, we know that U RMS is the highest, which is root 3 RT by M. Then comes U average, then comes U MP. So U MP is that point where you have maximum number of particles. So you can see fraction of particles most probable will have maximum as compared to that of, oh, I made a mistake here, average, compared to that of average and compared to that of root mean square. Okay. And if you see the values, you know that URMS is more, and if I take the ratio, that would come as root 2, 8 by 4 and root 3. Okay, so that would be the 1 is to 1.112 and 1.225. This is what you will get it as the ratio. Okay, the ratio as well as this part, you know, directly as mains questions have been asked a lot of times, so you better remember this. Now coming to the most probable or any speeds, if you observe one thing, when I write dN by N, it is proportional to root of M by T in both U square function, also, as well as exponential of under root of M by T. So you will always get this as M by T for sure. In the overall equation, when we write the Boltzmann's curve, we always get it as root of M by T. I told you while writing A and B also that y is equal to 4 pi A x square exponent of minus B x square. I told you there also that this A and B both will depend on M by T. So for example, If you have m by 2 value changed, okay, so imagine this. These two are at two different temperatures where T2 is greater than T1. So T2 is greater than T1 for the same gas. So which value will be more here? M by T, if you check out. M by T1 and M by T2. Which value will be more? This will be more because T2 is greater than T1. In that case, if M by T value is more compared to that of M by T2, which means this should be more dominant in the parabola and less dominant in exponent form, because in the parabolic function it is helping it as it increases. Check out 4 pi m by 2 pi rt whole raised to power of 3 by 2 u square. This is the parabolic part, and e raised to power of minus m by 2 rt u square. This is the parabolic part. Sorry, this is the exponent part. So in the parabolic part m by t ratio अगर ये बढ़ जाएगा तो ये पूरा टर्म का वैल्यू बढ़ जाएगा. Adya, connected back? Yeah. Okay. Check this. What I'm saying, for A and B, if you check out, m by t ratio, if it increases, then this function will increase. M by t, if this increases, this function will decrease. So check out, that is what we are saying. If m by t value is more, the parabolic part is increasing, but exponent part is decreasing. Okay, everybody understood that? Originally, if you consider T2 by T1, I mean T2 and T1, m by T1, m by T2 दोनों को compare करो. M by T1 is greater than M by T2, which means this is and M by T, if it is more, then parabolic function will dominate, exponent function will be less. Remember only one part of it, that should be helpful. Is this clear, everyone? For different gases, if molar masses are different at same temperature, then M1 by M2, M1 by T, M2 by T, if you consider, and if M2 is greater than M1, right? Then here this M2 by M1 वाला part dominant होगा parabolic पे, and then less होगा exponent पे. So this should be M2 वाला graph and this should be M1 वाला graph. I guess this point is clear. So these are the direct equations asked in JEE Advanced. Got it? Like what happens in case if you have parabolic function. See, at low pressures, at low speeds, parabolic function will dominate. So if temperature is increased, this is for the same gas, molar mass same hai. If only T increases, number of particles will decrease for parabolic part. Exponent part, number of particles will increase. Got it? This is at low, as the temperature increases. Okay. You can see that as the temperature is increasing, ये कर्व नीचे की तरफ जा रहा है ना, ऐसे नीचे चला जा रहा है. Same way, same temperature, different gases. मोलार मास इंक्रीज हुआ तो dn by n इंक्रीज होगा पैराबोलिक पार्ट के लिए, और dn by n डिक्रीज होगा एक्सपोनेंट पार्ट के लिए. Different temperature, different gas, then just check out m by t ratio. If m by t ratio is more, parabolic part dominates. M by t ratio is more, exponent part will be less. Okay, so this was asked in 2003. Got it? To plot the graph for these four cases. Okay, so SO2, you know, at around 300 kelvins, SO2 at 150 kelvins, SO2 300, O2 at 300. Check out for all of these cases, how would I plot it? First case. Okay, I will first write those two and see which one is more matching. Best part is check out m by t ratio. M here is 64 divided by 300. Here it is 64 divided by 150. So obviously this is more dominant value, right everyone? So since this is more dominant value, तो ये वाला कर्व B का होना चाहिए, ये वाला कर्व A का होना चाहिए. So this would be B and this would be A. I suppose all of you understood that. See the second curve. Now this time temperature is same, molar masses are different, and this molar mass would be more. So you can easily make out, suppose if you have these two curves, then this should be for SO2 and this should be for O2. Yes, that is clear. See the third one. If you have SO2 400, so which means 64 by 400, and here it is 32 by 200. The ratio is coming out as same. This is also 32 by 200 only. This is also 32 by 200, which means both graphs are one and the same. So A and B, both of them are same. Fourth one, SO2 at 500, O2 at 300. So this is 64 by 500 and this is 32 by 300. So you can see this value is dominant because this is 32 by 250. So which means if I put these two graphs, this would be for A, this would be for B. So everyone please look over and let me know if you have any doubt.